Right, so now we're going to talk about the Crank-Nicolson method. All right. So previously we had talked about the implicit and explicit discretization of the heat equation, right? So let's think of the implicit and explicit methods as being part of a parametric family of numerical methods by the following. So consider sort of the implicit and explicit discretizations as part of a parametric family of methods of the form here. So what I'm going to do is essentially I'm going to interpolate between the implicit and explicit methods. Okay, so I have a theta, which is this interpolation parameter. Okay. All right. So essentially what happened is that you have two different sort of difference operators. It's like corresponding to the second derivative, and it's a question of whether you differentiate, whether you compute the second derivative at the previous time step or the current time step, right? Or well, sort of the time step where you already know the initial data, it's like versus the time step you're trying to compute. Okay, so what I'm doing is I'm interpolating between the two of this, and then I'm still using this sort of first order finite difference approximation of the time derivative, right, which is given here. Okay, and you know, sort of easy to convince yourself that when theta equals to 0, we recover the explicit method. Possibly up to reindexing. And then when theta equals to 1, it's like we recover sort of the implicit method. And again, as I sort of alluded to before, one way to think about the explicit and implicit methods are that you do a semi-discretization of the PDE, where you first discretize the spatial derivative operator with this sort of second order central difference operator. And then you get a system of equations and you discretize that using either the explicit Euler method or the implicit Euler method. And they will give you these methods which you talked about before. Okay, so an interesting special case of this parametric family, it's like of methods, is when theta is equal to 1/2, right? So when theta equals to 1/2, right, we get what is known as the Crank-Nicolson method. And along this line of semi-discretizing the differential operator and then discretizing the in time via a numerical method, numerical ODE method, the Crank-Nicolson method can be viewed again as a semi-discretization and then applying the trapezoidal rule to the semi-discretized system, right? So this can be viewed as coming from sort of semi-discretizing these spatial derivatives. And then applying the trapezoidal rule. To the resulting system of equations. Okay. All right. So anyway, so this is what is called the Crank-Nicolson method. So let me write this formula down. It's like as we have done before, in terms of this S parameter, right, which is k divided by h squared, right? So S equals to k divided by h squared as before. And then what we're going to do is that we're going to put all the values of v, it's like corresponding to time slice j, it's like on the left hand side, and all the values corresponding to time slice j minus 1, it's like on the right hand side. Okay, so that's what we're going to do next. All right. Okay, so with that simplification involving s, we get minus svi minus 1j plus 2 plus 2s vij minus svi plus 1 comma j is equal to svi minus 1 j minus 1 plus 2 minus 2s vi j minus 1 plus svi minus 1 j minus 1. Sorry, j plus I plus 1, sorry. Okay, all right. So, yes. So you can write this system of equations as before in terms of this capital V, which is a vector. It's like for fixed j, it's like in variable I. Okay. And when you do that, you can write this equation as 2 times the identity plus SB Vj is equal to 2 times the identity minus SB, it's like times Vj minus 1, right, where Vj is this vector of V1j all the way up to Vnj, and then V is this matrix involving 2's along the diagonal, and then a minus 1 above and below that. Okay, so so by now it's like you should know what the plan is, right? You have this relationship. I can write Vj in terms of Vj minus 1 by inverting this system of equations, all right? So this tells me that Vj is equal to, how do I want to do this, right? 2 times the identity plus SB, inverse acting on 2 times the identity minus SB, acting on Vj minus 1. Okay, so as before, it's like if this entire matrix, right, has a spectral radius which is less than 1, it's like this method would be stable. Okay, so we want row of 2 identity plus SB inverse times 2 identity minus SB, right, to be less than 1. Okay, so this condition is that, so if mu1 to mu n are the eigenvalues, of B, right, then this requirement is equivalent to, so it becomes the following, 2 plus S mu I inverse 2 minus S mu I in absolute value, right, is less than 1. Okay, so because mu I is equal to 2 times 1 minus cosine theta I, right? So this is something we've established before. It's like the eigenvalues, it's like of this matrix B, right? This implies that mu I is between 0 and 4. And then from this, you can show that this inequality always holds, okay? And can show with a bit of work that sort of the inequality always holds. And of course, if the inequality always holds, then it means that the Crank-Nicolson method is unconditionally stable. Okay, so right. So with that, Crank-Nicolson is unconditionally stable. Sort of independent of S, K, and H, right? All right, so stability is great. I mean, it's like that's sort of the bare requirement, but it's not necessarily enough, right? So we also want to ask whether the resulting answer is accurate, not just that it doesn't blow up, okay? So what we're going to do next then is to do some error analysis to show that the Crank-Nicolson method converges. It's like at least if you know, it's like refine basically both the spatial and the temporal mesh size. Okay, so let's talk about that in a bit.